Right. Welcome everyone to another OCP-TAP call. This will be call number 115. And today we have a presentation by Julian. Julian's presentation will be about like DPLL over fiber for low-cost two-way time transfer. So as far as I understand, it's basically a low-cost solution or low-cost alternative for white rabbits, pretty much. And uh, as usually with the format, uh, Julian is a network hardware engineer at Meta. Prior to Meta, Julian worked at A10 and Cisco as hardware designer, which he worked on network hardware appliances. Julian has been very active on the OCP-TAP project, supporting multiple work streams, all all the evolution of time card with the newest features, as well as like I can attest to a lot of other things like time had, time stake, the list goes on and on. So we'll spare that for now. So Julie, I think a lot of you guys are familiar with Julian's work on PFM. And I mean, this recent work that he's going to present more details about, which is about like getting DPLLs to do the time dissemination or synchronization and synchronization like over fiber. So with no further ado, Julian, the floor is yours.
Very good. Thanks, Ahmad. So my presentation today is about an architecture I came up with. I called it DPLL over fiber. So DPLL over fiber for low-cost two-way time transfer. And for this work, I collaborated with Greg Armstrong and his team at Renaissance because I mainly use their DPLL architecture, and also with Ahmad here. So kind of let's start with like a motivation. Why did I even come up with a new architecture? You're looking at the way that two-way time transfer works today. PTP can do it to the sub-microsecond level. So we're all familiar with that being part of the TAP community. And at the cheapest level, we recently released the time stick, which I didn't include a picture of here, but is basically a USB to Ethernet dongle that can do PTP and has a PPS output. So you can measure sub-microsecond or even low double-digit nanosecond time transfer with PTP. So this is a relatively known solution. There's lots of existing architectures out there for PTP. But if you talk about sub-nanosecond domain, obviously, if you go better performance, you have to pay a cost, right? So the most prevalent architecture in the industry today is White Rabbit. So the pictures on the right, well, the top one is from a commercial White Rabbit solution from Saffron. These are based on pretty high-end FPGAs with lots of transceiver ports. And they're mostly 1 gig Ethernet, but 10 gig also came out recently from Saffron. And they're relatively complex FPGAs since they're doing a lot of the phase detection, PLL, soft PLL inside the FPGA, as well as interfacing with transceiver ports, which are also fairly complex. But when I talk to people in the industry about, or even Saffron, when I ask them, well, how is White Rabbit used? Maciej at CERN said they use White Rabbit for data, but pretty much everyone else, finance or other industries, use White Rabbit in parallel to a data network because the bandwidth isn't keeping up with traditional Ethernet bandwidth. So Ethernet networks today have pretty much starting at 100 gig is pretty common, but all the way up to 400 gig or 800 gig links. And so White Rabbit is typically deployed in parallel with a data network. So you have a front-end data network running at, say, 200 gig. And then you have your White Rabbit devices in parallel to that using different fiber, different transceivers, different devices, coax. And so my thought was, well, if you're only using White Rabbit for time and frequency distribution and you're not really using it for Ethernet or data, why are you paying the cost of such a high-end FPGA with all this overhead of Ethernet framing and packet forwarding and everything like that? So my goal was to come up with a low-cost solution that can do sub-nanosecond time distribution and also measurement. Measurement is kind of a different field. I'll touch on that a little at the end. But basically for time distribution to get to sub-nanosecond region, is there a cheaper way to do it than doing the White Rabbit approach? And yeah, my open disclaimer at the bottom there is that I have no problems with White Rabbit. Maciej gave me a very nice shirt, which I wasn't planning to present today, so I didn't wear. I was planning to wear it when I gave this presentation. But yeah, I have this shirt and I wear it a lot. And I also developed a White Rabbit NIC with Ahmad and Alex and Maciej to have a kind of lower cost White Rabbit capable end node that can do 10 gig N potentially 1 gig. So just open disclaimer. So let's talk about a little bit about what a DPLL is, just for people who aren't aware. So at a high level, a DPLL is a digital PLL, but what that means is it's a very powerful clocking ASIC that can take multiple inputs and generate multiple outputs. A lot of the diagrams and notes and text that you'll see in my presentation today are from the Renaissance Clock Matrix data sheet or app notes. And so these diagrams on the right are the kind of high-level block diagram of what's going on inside of their DPLLs. At a fundamental level, they can generate multiple output frequencies from known input frequencies. So for instance, in that top right picture, if you know that clock 0 is a 10 megahertz input, it can generate all the Q outputs basically at an arbitrary frequency sourced from that 10 megahertz input. And a core feature of modern DPLLs is they have a lot of 1 PPS capability. So they can synchronize outputs to a 1 PPS time input and frequency input. So if you have your 10 megahertz input and a 1 PPS from, say, a GPS receiver, and you want the output to be frequency traceable to the 10 megahertz, but also edge aligned to the 1 PPS, these DPLLs can handle that alignment in time and frequency. And then the bottom right is kind of like the basic block diagram of a single channel. So in the top right, it shows that there's 8 DPLLs internal to 1 DPLL chip. And each DPLL as a discrete component is kind of built up of these main building blocks for building a locked loop. And so to kind of break down into the 2 main components that I needed for this architecture, one is the TDC, which is the time to digital converter. So this is, in a normal PLL, you have a phase detector, which gives you your error signal. And in a DPLL, it's the same, but that error signal is generated in a digital domain. So what they do is they can generate a error signal at approximately 50 picosecond resolution between 2 inputs, or 1 picosecond if you give it time to decimate and average down between 2 inputs of the same frequency. So if I have 2 10 megahertz inputs, for instance, it will generate a digital representation of the time difference between edges of one versus the other. And that it uses as the error signal to its closed loop to discipline an output signal to the input. The input TDC on the Renaissance chip as well can be used in basically a measurement mode similar to an instrument where it can measure between 2 devices. It doesn't generate any outputs from it, but it will measure the phase difference between 2 input signals, even for 1 PPS signals down to 50 picoseconds. So you can measure 1 PPS to another at approximately 50 picosecond resolution, or 1 picosecond if you know that they are frequency aligned and not drifting with respect to each other. And another key feature is that they have a time of day feature. So this is similar to an Ethernet PHC, where you have a counter basically that represents seconds, nanoseconds, and sub-nanoseconds. And this feature is used later for some other things, but it also allows you to do time stamping with respect to that PHC. So similar to some Ethernet NICs that have an external SMA input for PPS input, and you can get a timestamp of the external event with respect to the clock on the NIC, the DPLLs have the same capability. And so to talk about what the architecture is, first I had to break it down into the major components for two-way time transfer. Probably a lot of people on the call, this is not new information, so I'll go over it a little bit quickly. But for stable two-way time transfer, you need to have the time signal, the second point. Basically, okay, here's the time, an edge or a timestamp, and then the value of that time. But you also don't want to drift in between those time events. So they're probably not coming all the time. You need, say, in the PTP network, you have 16 packets per second. That's still a relatively large time in between each packet, and you want to have a stable frequency if you want to have very stable time transfer. So the first point, stable frequency signal is typically done over Ethernet with SyncE. White Rabbit does the same thing. They extract a frequency from the Ethernet signal and cover that out as typically 125 megahertz or 156, depending on the speed. And then in addition to that, this is a nice to have, but it's also kind of important for two-way time transfer deployments, is you need some kind of information about the clock. So this is typically a data signal packets or some other data method that one end can tell the other what time and frequency it's sending. So this can be things that like PTP messages have in the announce message. So clock quality, how traceable they are, but also the time of day. You want one end to know that, okay, it's 2024. You need to transfer that data over some mechanism. It doesn't need to be very fast. It doesn't need to be very high bandwidth, but it does need to have some mechanism of giving data with respect to the time and frequency signal it's sending to the other end. And so if you kind of break that down into three components, and then you look at how those relate to a DPLL, as I described earlier, frequency transfer is basically the easiest. I don't need to spend too much time on this. A DPLL is meant to take a frequency in and generate a frequency out from that. So it's kind of the core functionality of the chip. So I don't really need to do much to do frequency transfer with the DPLL. But the only side note here that I give, which you'll see why I give it here, is that low speed SFP, so 1 gig or 10 gig transceivers, LR, SR, BiDi, DWDM, all of these transceivers, they don't tend to have much in the way of signal filtering. So their frequency transfer curve is actually quite low. It'll pass a very low frequency signal even. So you can put a 10 megahertz or 25 megahertz signal through a 1 gig or 10 gig SFP, and it'll pass through cleanly to the optical domain and then back to the electrical domain. So as far as the electrical to optical conversion goes for a two-way time transfer system, standard SFPs can do the job. Time transfer, it starts to get a little more complex. So time transfer relies on a feature in modern DPLLs called ePPS. This is where a 1 PPS edge is associated with an edge of a clock signal. There's two different mechanisms for this. I won't go into the details, but basically what it is you adjust the PWM duty cycle of the clock to associate a rising edge with a 1 PPS signal. So for instance, if your duty cycle is typically 50% and then you have a 1 PPS, you want to demark on the clock what that edge was, you'll change the duty cycle to say 25% or 75%. And the DPLLs can then recover that out. They'll know, okay, that rising edge then had a duty cycle of 75%. That was the 1 PPS edge. And so they will be able to extract out that 1 PPS as a discrete 1 PPS signal. So if you have a 25 megahertz with 1 PPS embedded, the DPLL on the input side to the DPLL can then generate on the output two outputs, one as a frequency 25 meg or 10 meg or anything else, but then also the 1 PPS signal extracted from that frequency input. This is a very important feature. And for small data transfer, this one might take a little bit to explain, but I wanted to get this on the record. So this part, this part is only necessary if you don't have a out of band network for DPLL over fiber. But if you want to do everything in band, let's say you want to be resilient to PTP spoofing or Ethernet man-in-the-middle attacks or something like that, then this kind of closed DPLL network can support data transfer at a low bandwidth rate. Basically, it uses a feature of the Renaissance DPLLs that encode frames into the PWM. So instead of just having one edge of the clock be adjusted duty cycle to demark PPS, they will adjust multiple edges with a modulation shown in the top right and basically make a frame of it. So the first edge, I believe, is the PPS edge, and then after that is frame data. So there's two mechanisms that they implement on the commercial clock matrix chips today. One of them is a TOD frame. So every second that you have a 1 PPS out, it will also encode a TOD frame after that with 6 bytes of seconds, 4 bytes nanoseconds, 1 byte sub nanosecond. And the reason I put these notes about time is I basically abuse this mechanism. But basically 6 bytes of seconds is 8 million years, right? And the chip came out in 2020. So I don't really need to represent like 8 million years in time. And even 4 bytes of seconds gets me 136 years. It's a pretty long time. So I basically assume that I can rely on 4 bytes of seconds and abuse the upper 2 bytes for my own purposes, which I'll go into in the next slide. But the other mechanism that they implement in the DPLL, which I use mainly for the kind of data transfer, is the FIFO. So they allow you to send or receive 128 bytes over the clock using the PWM mechanism. And this is kind of done transparently to the user. There's only a couple registers that you have to manipulate in the chip, but they will allow you to send or receive up to 128 bytes from the far end. And so I implemented kind of a two-way time transfer protocol with these two mechanisms. This slide's a little bit to describe, but I wanted to also get this on the record, was if you have the FIFO mechanism as described in the current clock matrix chipsets, it's a little bit clumsy, I would say, to implement like a really robust bidirectional data transfer. because the FIFO is created as basically a single FIFO. So you have typically in an Ethernet chipset, you would have a transmit FIFO and a receive FIFO, and they would be independent. In these chipsets, the FIFO is shared. So transmit and receive are the same memory region. So how do you know when you're transmitting to the far end or when you're receiving? You have to physically tell your own side, okay, I want you to set up your FIFO as a receiver or as a transmitter. So you have to kind of negotiate with the other side who's transmitting or receiving at any given time. So this is where I basically abuse the upper 2 bytes of the time of day, which kind of happens regularly all the time. So I made a kind of handshaking protocol over the 2 bytes of upper time of day. Again, this is not for high bandwidth data or anything, but it will work given enough time. And so I have basically the upper bit, which is, like in the 4 million year significant range or something like that in terms of seconds, as basically a flag. Like, am I abusing the time of day for data handshaking or not? So if you have that set, then you have like a handshake flag. Okay, I'm trying to talk to you. I haven't seen your response, that kind of thing, similar to TCP handshaking. And then the bit 4, I kind of made as a kind of signal to the master from the follower that, okay, I'm following you now fully. And then the other 4 bits I use as a transaction ID. So there's not too many data fields that at least I'm defining right now, but certain things like you want to query the input status. So, okay, you have 10 inputs to the DPLL. How many are locked to what frequency, something like that. Or you want to query just the name or the MAC address, some kind of predefined transaction IDs. And then the other byte I use as basically a collision negotiation byte. So because you have such high latency between the two sides, if they both want to talk to the other side at the same time, you need some kind of way to handshake who's going to do it. Well, if you have like multiple seconds of latency between each other, I basically made a random byte, and whoever had, I think I made it the lowest byte wins. So you know what you're sending to the other side. You see the other side is sending you a byte saying, hey, I want to talk to you also. Okay, my byte was lower than them. I know I won, and I will start, getting ready to transmit, something like that. And so with this mechanism of time of day kind of abuse and then the FIFO mechanism, you can create a slow but coordinated data channel that can send up to 128 bytes at a time, kind of with negotiation also of what that data is. So you can have kind of known fields, but you can send data back and forth over this DPLL network in an isolated way from any kind of Ethernet network. Another key part that I wanted to touch on was, what about system level implementation? So let's say I go through all these slides and you're impressed with the two-way time transfer, but you think, well, this is just some mechanism for doing two-way time transfer. What about all the other problems that come with system reliability? You want failover, you want redundancy, monitoring, all these things. And I kind of wanted to highlight that a lot of those features are kind of inherently present in the DPLL these days. There's a lot of notes on the side of the slide that are basically screenshots of the datasheet from Renaissance. But if you think about the things that you want to have in a two-way time transfer system, two-way time transfer including frequency, you want to have some operational capability to go into holdover when a reference is lost. You want to be able to know, okay, is my input good, or is it drifting more than another, or is it even there? And you want to be able to switch between different inputs based on, okay, is the signal there? Is it a good quality? And then also have mechanisms to go back and forth in a deterministic way. Okay, this input is probably the best, but if it's worse than another one, I'll fall back to that one. Or if it dies, I'll go to the second one, something like that. So those are basically the first 3 features there. Is the Renaissance DPLL has fairly advanced holdover capability. It could be improved with software implementation, but it does have hardware functionality for holdover operation, including history of previous phase measurements into an average holdover value. It will monitor inputs for quality and presence. So are they still there at 10 megahertz if this thinks it's 10 megahertz? And also, is it drifting at a certain rate more than it expects? It will disqualify it. Automatic switchover kind of ties into that. If the input is bad, you can tell it the order of inputs that you want it to switch between. The other feature that I think is kind of special with DPLLs is the hitless switchover, which is, I'm not sure how White Rabbit does it, honestly, so I won't speak on that, but at least this capability in DPLLs lets it slowly adjust to a new input. So if it was tracking, say, one atomic clock, that atomic clock dies, and you have another input that it's switching to, it can slowly either drift to that, like slowly discipline to that, or it can keep the output stable and then just have the frequency input feed the output. So this is done by holding the phase that it was doing with the previous one with respect to the second source. But then the output shift is basically a glitchless, hitless switchover is why it's called hitless. So your output is not affected by the fact that your input switched. And then basically as another kind of input qualification or output qualification, let's say you have a output source that you don't want to unlock, for instance. The DPLLs can have a phase change limit, so they can prevent a certain amount of slew on the output. This can be specified, one of the notes here. You can do like 1 nanosecond per second, so the output will only change by 1 nanosecond per second, or all the way up to basically uncapped. So depending on your application, this might be a useful feature if you want to have a certain amount of stability in the output, even when you're switching between inputs, let's say, or different sources. And so my key point here is that all of these features let you build a system architecture out of DPLLs alone that has the kind of failover redundancy and monitoring that you would expect from production two-way time transfer system. And it's all built into the hardware. It has automatic failovers and configurable redundancies already in the chipset that you can configure at any time, or you can have it be configured at boot up time through an EEPROM download. So this is the hardware design that I built to prototype this. Took me quite a few spins to figure out how to connect a DPLL to SFPs. No exact reference design for that. So the core parts of this design are a I225 NIC. So this is basically my PCIe bridge to the board. I use the pretty much top end DPLL from Renaissance for the clock matrix product line, so 8A34001. And then 4 SFPs. So each of those SFPs is connected to a DPLL channel, either input or output. So 4 differential inputs to the DPLL, 1 for each SFP, 4 differential outputs for the DPLL. There's a SIT 5501. It's the kind of gray square above the inductor on the right side of the board. This is a 10 ppb local oscillator. These are available on DigiKey and they fit nicely on board, so I've used them a lot. There are 2 SMA inputs, mainly because I ran out of front panel space, but those are configurable from the DPLL as input or output with multiplexers on the board. So there's 2 input channels on the DPLL, so you could use both SMAs as inputs, or you could use both SMAs as outputs. And there's a bunch of UFLs on the board, if you can see kind of near the top of the board. Those are connected to either unused pins from the DPLL, or a lot of DPLL outputs are differential, but I only use one end. So the other end will be connected to a UFL for measurement purposes or calibration. I also included a clock buffer for PFM to buffer the 100 megahertz PCIe clock to the DPLL. I didn't implement that on this board so far, but the hardware capability is there. And there's a M.2 GNSS slot with the pinout that we defined through OCP for a M.2 GNSS receiver. So in theory, you could put a GNSS on this board and have it disciplined to GPS. And so to kind of go in the details of how the time transfer works on this board, the signal over the SFP is a 25 megahertz. That's the fastest clock that you can generate from clock matrix with PWM. So it's 25 megahertz with 1 PPS embedded and PWM time of day for frequency, time, and data. But then the tricky part is, how do you do the delay compensation? So you have some SFP link over fiber. You need to compensate out the one-way delay from the leader to the follower. So the mechanism I used was kind of like a sacrificial channel, I called it, in the leader board. So what you do is your leader board has some reference inputs. In the diagram, I drew a 1 PPS 10 megahertz. It then sends that as a 25 megahertz with embedded PPS to the follower board. The follower board then on the same SFP link sends back what it's receiving from the master, from the leader. And the leader then picks a channel inside of itself to follow the follower, basically. So the leader is listening to what it's getting back, and it's extracting out the 1 PPS from the follower after going through the total round trip. And it's basically looping that back to itself in order to use the input TDC to do 1 PPS measurement. So in order to do the full calibration, you need 2 measurements. One is the round trip delay. So the leader needs to measure, this is the way I implement it, at least. There might be another way. but the leader needs to measure the round trip delay. So its estimate of how long it takes for its signal it's sending to the follower to come back. So for that, I drew the two little squiggly arrows. One is it loops back its PPS from the transmit PWM channel to itself. And then it also loops back the 1 PPS that it's receiving from the follower to itself as well. And on the input TDC, it can then measure that in with respect to each other down to 50 picoseconds or even 1 picosecond because they are frequency aligned because the follower is following the leader. And then the second measurement you need is you need to know the offset of what the reference is, kind of your golden 1 PPS, to what you're sending to the follower. So this, in the beginning, when you first turn everything on and there's no calibration, they will be identical. You just lock what you're sending to the follower to your reference input. But if you want to have the follower PPS output be the same as the reference, you have to measure the error signal of that round trip delay and then adjust the PPS you're sending to the follower to be half the round trip. So the error signal that I measure in software is the second measurement. So what you're sending versus what you're receiving, or the reference versus what you're sending, minus half of the total round trip. So you basically adjust the 1 PPS that you send from the leader to the follower to be halfway between the total round trip of the reference to the follower. And I did this by slowly frequency incrementing the leader output to the follower to introduce small time shifts over time. So I would put a small frequency shift and then get rid of it, and then measure again, frequency shift, get rid of it, and then measure until you get basically down into the noise floor of the 1 PPS measurement of the DPLL. And then from there, you're able to have stable two-way time transfer compensated for the round trip delay over an SFP. And then at that point, the follower 1 PPS would be aligned to the reference 1 PPS. So kind of one other point I wanted to make was, well, what about, Ethernet or your host that you're connecting this board to? I'm kind of proposing basically a non-Ethernet closed network between DPLLs. It's not really backward compatible with anything as far as I know, unless you implement that in the FPGA, which is a different problem. But the I225 that I put on the board, I kind of used that as, this was Nobu's suggestion actually, as a bridge to kind of existing networks. So the I225 provides access to the Ethernet domain and the PCIe PTM domain. The way I made this work was, this is actually how I made the board work, was SDP, the 4 SDPs on the I225, 2 of them I use as bitbang I2C. So there's a kernel driver I wrote to basically control the SDP pins as I2C to control the DPLL. So I don't need any other interface chip over PCIe. But the SDP0 and SDP1 I use as basically the time mechanism to get time from the DPLL to the I225 or the other way around. So one is the input to the DPLL and one is the output from the DPLL. So you can either have the DPLL get a 1 PPS from the I225, which is either from PTM or PTP, and then discipline the DPLL to that, or the DPLL network can provide 1 PPS plus time of day to the I225, which can then discipline to that and then bridge that into the PTP network or the PTM network. So with that, this architecture can kind of go backwards into a normal Ethernet network, or it can go over PTM to a CPU, which can then distribute it over PCIe. So looking at the hardware implementation, this is a picture of my home setup. I have 2 boards, 2 of the same board going over a 10 gig LR transceiver to each other. This picture I think I took after I kind of tore everything down, but I had a Swabian time tagger next to both boards measuring the top SMA out of both boards as a 1 PPS output. And after doing basically that round trip compensation, I stopped running any software and left it for quite a few hours. And I was able to measure the graph on the right, which is the time transfer time error between the 2 boards without any cable delay compensation. So the time offset is centered around 0. And at the extremes, it goes between basically minus 300 and 200 picoseconds. But the majority of the samples are within plus minus 200 picoseconds. And then the kind of error of the instrument itself is about 34 picoseconds. So this gave a fairly robust time transfer mechanism over fiber that was pretty low cost and got me down into the sub half nanosecond time transfer range. And I should note that there's a lot more optimization that's capable with these DPLLs. I didn't play much with, say, the loop filters, loop bandwidth, all of the more complex features of a DPLL. They're a little outside of my scope, but Greg and his team, I'm sure, could get this performance to be much stabler and cleaner, given time kind of to optimize your loop parameters. And so then kind of, well, you have two-way time transfer between two boards. What do you want to do with it? Either you can have the 1 PPS out, same as White Rabbit, and do whatever you want on another board, let's say. But I was kind of thinking the board has other features. You can, for instance, use the input TDCs to measure two 1 PPS signals down to 50 picoseconds if they're stable. Or it has the time of day feature, which can timestamp inputs similar to an Ethernet NIC to, say, 1 nanosecond resolution. So if on the SMA, let's say you feed in some external event or 1 PPS, it can then tell you with respect to its time of day inside the DPLL, when did that event happen, to give you basically a timestamper input. And there's a lot of extra UFLs on the board that you can also use for inputs or outputs. The fact that I put 2 SMAs isn't necessarily a restriction of the DPLL, more a restriction of the PCIe form factor. It can also do frequency measurement. So the input TDCs are set up as continual phase monitors. So you can have one input, say, is your frequency reference, and then you can lock to another frequency reference, and you can see kind of the phase that the DPLL disciplines with to do a phase estimate of the frequency offset between two devices. And at a core level, just the DPLL can give you kind of arbitrary output frequencies from 1 pulse per 2 seconds all the way up to 1 gigahertz. And there's additional outputs on the board that are capable of that. So there's a lot of different features that on the DPLL itself, beyond just the two-way time transfer, that also make the board and the chip a very diverse user of time and frequency. And that's the whole slide.
Wonderful. Thank you, Julian. So let's go for some questions. There is one in the chat from Kaylan. I don't know if you already answered it, but have a look at it.
How are you putting together info to send across the DPL? Oh yeah, so that's kind of why my slide not going. Okay, that's why I kind of outlined this in detail. So if you if you really want to know the inner workings of this thing, so this was just a protocol I came up with, completely arbitrary. Basically, like I described earlier, you have a FIFO mechanism for 128 bytes. But you can only read or write for it at a given time. It can only be set up as a read mechanism or a write mechanism. So you need some way between the two sides to negotiate who is receiving and who is transmitting. But both sides are constantly sending time of day information to the other. So I basically change in the DPLL, I step the time of day to kind of corrupt the upper bytes of the time of day, which are not useful because they're talking about hundreds of years in the future, and use those as kind of like spare bits to kind of handshake or negotiate who wins access to transmit or receive at any given time, if, let's say, both sides want to at the same time.
Okay.
The code for that is online. It's kind of gory, but I did test it and it worked. It does have, quite a bit of latency because you're negotiating over basically 1 packet per second from both sides. So
you're using the DPLL outputs basically just as like the clock signal is being transferred directly to the SFP over, what is that? The ZOwie interface or something?
So the SFPs alone are fairly straightforward. They pretty much just take a differential LVDS input and convert it to optical, give you LVDS output. So that worked once I played with the termination scheme well enough. It pretty much worked straight out the bat, like a fast enough frequency from the DPLL as a differential output pretty much goes through the SFP clean.
Okay.
So the optical part is pretty straightforward.
So it's not a Ethernet packet that you're sending. You're just sending a clock signal and then doing this PWM
Correct.
scheme. Okay.
Correct. Yeah. So that's what I meant, that this is kind of like a parallel network, not even Ethernet, basically a clock with stuff on top of it. But that stuff on top of it lets you build kind of like a data transfer or pulse per second transfer.
Yeah, I guess I never really thought about using the SFPs for anything that wasn't Ethernet protocol, but that's an interesting way to do it. That's cool.
I wasn't 100% sure what the low pass or high pass cutoff was for SFPs, but it worked out fine. So
So maybe like a question in terms of like, let's say, scale. Like, do you see like how do you see, like, if you want to scale, let's say, one like time source or leader to multiple, like, can you have also things like, let's say, boundary clocks or transparent clocks, things like that?
um, I would say they're all kind of boundary clock because they're taking it and then regenerating it out. So they all kind of add to the path delay, path degradation, whatever you want to call it. But the fact that it's all tracked through hardware gives you the kind of precision to get down into the sub-nanosecond range. The reason I built the board with 4 ports was basically you need 3 ports on a design to get to a network, right? You need an input and then at least 2 outputs. And I figured I might as well do one more. If I wanted to build a bigger board, let's say like a switch of this like design, it would be a different architecture from this. You would have to kind of like layer DPLLs, like you'd have like front IO DPLLs or something, and then like a core one that's the master or something like that. I didn't really want to go into that because that's more of like a ecosystem or hardware architecture problem as opposed to like a proof of concept architecture problem. But I don't see a reason why you couldn't build a kind of like tree or network topology out of this. Again, you would probably not want to use the in-band data transfer mechanism that I developed because of the low bandwidth of it. You probably want to would manage that network with Ethernet, let's say. But depending what your use case is, it would still be possible.
Hank is asking if there is any commercial product based on this. Have you seen anything? Or I'm assuming this is new, right?
As far as I know, like I said, nobody's connected DPLLs or just clocks to SFPs. And I think I read one post online when I was developing this about somebody putting 10 meg over an SFP, but they didn't talk about like PWM or PPS or like PWM data or anything like that. So I don't know anybody who's built anything like this, and I've never seen any reference design or any similar design in the industry.
All right, any more questions?
So,
Maybe I can ask another
Julian,
one. Oh, sorry, go ahead. Go ahead.
sorry.
Go ahead, Zoltan.
So the protocol that you invented, it's actually you are included into the DPLL firmware.
Oh no, yeah. So, well, not to shade Greg too much, but I didn't pay them anything, so they didn't give me any custom firmware. So this is just using what's kind of off the shelf available. So they have register sets where the time of day counter, you can step it or add to it, absolute values. And then they also have the FIFO mechanism, which, like I said, you have to set up as either transmit or receive at any given time. So this was all done just kind of ad hoc. It's not done in the firmware. So I have to do the I2Cs transactions to basically change the time of day if I want to do this, handshaking, and then read it back, and then do the FIFO, read it back. So it's all done kind of with the normal firmware that's available. If you wanted to make it optimized, then you would probably want to do it in the firmware. But I wanted to see what was possible just with like off the shelf firmware components and everything.
How many times how often you are sending these messages?
The time of day is once per second. And then what I found was it takes kind of like once or twice or 1 or 2 seconds before you actually receive it. So you have kind of like a latency. If one side sends something, the other side takes like 1 or 2 seconds to get it just for this time of day handshaking. So, you have like a SYN-ACK kind of thing going on, and then like a teardown. So you have to like kind of go through that ping pong a couple times, do the FIFO transfer, and then do like another ping pong to say like, okay, I got it, I'm done. So I guess once per second is the answer, but it also takes more time than that just to do the overall transfer. Did I answer your questions?
So
Yes,
maybe
thank you.
maybe another question is like, how much do you rely on the two-way time transfer? Like, meaning like if you just do it one way, how much degradation you will have?
One way is the same, right? All the stability is from the one way. The two way is just for the offset calibration. So the 1 PPS and the 10 megahertz, you're basically receiving for free, even if you're just receiving it. But then if you want to actually align the 1 PPS, then you need the two-way mechanism.
Yeah, no, I'm thinking about all the scaling. So
Mhm.
you cannot do broadcast. So you need to basically you need to go back because you want to have like basically the compensation of the latency.
Right. I guess in that respect, it is different from Ethernet too. There's no concept of frames really. It's just like a clock with stuff in it.
Yeah.
So there's no way to do kind of like a broadcast packet or something. Every packet, time of day or FIFO is over a dedicated link.
Yeah.
So yeah, it's all point to point basically.
I think the only way to do per se, let's say the switch, I mean like one to many, basically you simply have a lot of these nodes staggered together, and then one hardware they're just peer-to-peer. And
I think you would want to think about what are you trying to do. If you're trying to do it for data, I wouldn't use this system anyways. I just was investigating what it is like to do in-band data. But if you wanted to do broadcast data, you might as well just use Ethernet or anything really.
I think it's not bad. Let's say if you have something like this, let's say built in the time card, to let's say you have a time card somewhere that you have access to GPS, whatever, all of these things. Similar to let's say what YY is trying to do, but then we do it with wired. And then it allows you to go to another card that is like doesn't have all the timekeeping, let's say expensive timekeeping, but it acts like a time card because it just receives all the time and the frequency from the main one. Something like that. I don't know. I just thought. So let's see what the audience have as for questions. Paul, do you want to ask a question, or is just like adding more clarification stuff?
No, I'm just joining in the thought process here. I think Julian has done an absolutely excellent job. I have some very practical questions, like which particular FPGA are you using? Do you know whether that's Intel or Xilinx?
There's no FPGA here. So
There
this
is
is
no
all,
FPGA. Oh, okay.
it's all DPLL.
Oh, so you've implemented all of this in software?
A lot of the features are already there.
With the hardware, okay.
Right, yeah.
So I did a lot of work on PLLs much earlier in my career, and I think I've forgotten most of it, but everything that you said resonated. The interesting thing here that I think you've discovered, which everyone is kind of touching on, is this point about building trees. I have said many times in some of the talks I've given that all time is a tree. You just have to pick your root. Now, of course, what you've identified here is that when you pick your root, you also have failover and other things to worry about. And I am skeptical that you can actually fail over very simply with just using holdover. I think the failover has to actually be transactional in some kind of way, and then you won't blow up the world that distributed systems programmers are trying to use to do their transactions. But I'm just speculating a little bit here, but to extend the conversation, we've still got 15 minutes left.
Or perhaps even creating a ring, you know, like in this case, because I mean, you're always correcting for things.
Rings work great. Rings are wonderful. But the problem is they're completely divorced from GPS time. They have their own time, which is going to give you it's going to give you race-free circulation of packets, certainly, which is useful. But if you try to,
you don't care about accuracy. Yeah.
You don't. Well, accuracy is not a term I use in my vocabulary. It implies a measurement against some background of time, which we know doesn't exist. But it does imply that, well, who is your source? It's like, who is going to be the follower, and who is going to be the leader? I think that's the central architectural issue.
Going to be a quorum.
So anytime you have a follower and a leader, you can have a chain of them, and if you can have a chain of them, you can have a tree. So yes.
Very interesting. Anyone else from the audience? In comparison, Julian, this with White Rabbit also doesn't use packets. So
They do. They use Ethernet.
it does?
Yeah.
Okay.
Pretty sure they exchange messages over Ethernet.
I mean, aside from the messages, like basically they just using like that specific message to go back and forth.
Like the Ethernet devices that you can buy, they also operate as like a normal switch. So they have to, inside the FPGA, handle like, MAC address table and forwarding and all that kind of stuff. So
yeah. I'm wondering how can we make this coexist now with, let's say, with packets as they go through.
I mean, that's why I put the Ethernet network on there, so you can sit on an Ethernet network. It's not really a switch, but you at
But
least
then
have
the
a NIC.
Ethernet network will connect via the RJ45, not via the fiber. Am I saying something?
Right.
Yeah. So, I mean, from the same fiber, if you can coexist with data exchange, let's say you have frames with data goes through, and you have frames that you can do whatever you want, and then, or like,
Yeah, David says DWDM is possible. I mean, there's tricks you can play in the optical domain.
yeah,
The DWDM, CWDM.
that's true.
One thought I had was to put a QSFP on here, so you have like 3 lanes as like 10
There's
gig or
one
something,
for this and
or
3
one for
data,
this.
yeah.
Something like that. I mean, there's other ways you can do it. I was mainly just interested in proving this point, but if you wanted to have a NIC, let's say, and you had 3 ports as 10 gig and 1 is this or whatever, you should be able to do that.
I'm
Is it-
thinking if this can resolve the problem of lack of an ASIC to run White Rabbit. I mean, this is not White Rabbit, but it can.
I think
fill
it depends on your use case. If you want the whole Ethernet network, but like Paul said, if you have a simple tree, you have a leader and follower, this is designed for that, right? And you can then make like a chain of it. If you want more complex or more ports, let's say, it would be a different hardware design than this specific design. So I think it depends on the exact use case you're looking for. But just for having kind of like a distributed two-way time transfer over fiber that can connect to multiple sources over fiber, you can do that with this architecture fairly straightforward.
Wonderful.
Julian, if I may ask a dumb question.
Yeah, sure.
What you're transmitting between the 2 units is over a fiber, and it's essentially just a clock signal. There's any data which you have is what you have superimposed on the pulse wave. I mean, pulse width modulator. Is that right?
Correct.
Okay. So if someone mentioned that you could send this over Ethernet, then I don't see how you can get the 1 PPS and the clock. I guess the message you can send over Ethernet, but the signal itself, the 1 PPS edge, how can you communicate that over the physical layer of the Ethernet?
Oh, yeah. So if you meant the point that I said earlier about, like just use Ethernet or something, I was meaning that the core link that you're trying to transfer is the 25 meg with the 1 PPS, right? That's what you're sending over the SFP.
Okay, yeah.
But
And
let's say
that's not Ethernet.
No.
Okay.
Yeah, if you look at it on a scope, it's literally 25 meg rising edges.
You gotcha.
But
understand.
I was saying, like, if you wanted to send, let's say, clock quality information, or you want to say send to, like, you have 2 machines, right, with this card in them, and both they're connected to each other over this DPLL over fiber network, and you wanted one card to know that the other card is now in holdover, let's say, you could do that using this in-band data communication, but it's very slow and takes a lot of management. Or you could just send an Ethernet like data message. Out of band
Essentially,
message.
it's out of this clock band. Yeah. Okay.
Right. So depending on, how often you want updates or what kind of updates you want, basically managing this network of time and frequency, you could do it in band, but that's probably not the most efficient. The most efficient would be to run some software on both sides that just talks between them and kind of manages the DPLLs.
Okay. So I can see almost using this scheme just to send 1 PPS and using the so-called out of band, which is the Ethernet, to send all the other information that you want, including PTP. if you can get the two 1 PPSs aligned, you just need a message to say, what is the time at the 1 PPS? And that you can do pretty well with PTP, NTP, semaphores, whatever. Yeah.
Exactly. Yeah. So even just the time of day information, the DPLL is designed to do that fairly smoothly, but it's also has some latency access in terms of like I2C, let's say. Let's say you're doing a lot of I2C to the DPLL to manage it for other reasons. You don't want to take up that time to just read the time of day when it got the 1 PPS.
Yeah.
You can do that also with the PTP, yeah. Or just Ethernet.
And here too, you still have the same religious fervor on assuming that the two cables are the same length. Or reciprocal delay, you're treating the one-way delay as 1/2 the round trip.
Are you talking about this one? Yeah.
Yeah.
So asymmetry is, there's not much you can really do about it. Yeah. So we
that's why I called it religious. So
well, I presented a paper with Francisco and Armando at ISPCS about a special type of transceiver that can get the asymmetry due to fiber down to very close to 0. That's a different discussion, but there are tricks known in the White Rabbit world for
calibration. Yeah.
For calibration, asymmetry handling.
Yeah.
And also the new type of transceiver that I found to basically try to have the same path delay one way versus the other over the same fiber.
Over the same fiber. Okay. Understand. Yeah.
Single wavelength, single fiber. Yeah.
Yeah. Single fiber, single wavelength transceivers do exist. So you can buy like transceivers that are bidirectional over one fiber and both directions use the same lambda.
Yeah. Okay. So it's some kind of a ping pong.
Right.
Okay.
Yeah. So you need some way of getting the estimate of the round trip time and then compensating for that.
Right.
In my design, I did that all on the leaderboard.
Yeah.
No particular reason. Just that's the way I did it.
I have a question. So Julian, can you go back to that slide where you showed the graph alongside your board that you created?
This one?
That one, yes, perfect. All right, so my question is, first of all, what is the vertical axis? What's the units on that vertical axis?
Vertical axis is just count. So
just count, okay.
I cut it off because the graph was too large, but basically it's like 4 hours of 1 PPS. So however many counts that is per bin. The bin width is about 1 picosecond, I think, but that's kind of within the noise of the measurement device.
Okay, thank you.
Sure.
Really interesting. That was what triggered my thought when I sent you, I put that link in the chat about the Huygens optics, because they have some very similar graphs on the recent YouTube video that looks pretty much exactly like this and deals with the question of what is the arrival time of a photon?
Yeah.
I mean, in this architecture, it basically depends on how well the phase detectors in the DPLL can extract 1 PPS out and then also measure that. So that's the kind of noise resolution that I get. And then this measurement is kind of a measurement of the noise of the swabian itself.
So have you put any thought into how indefinite causal order, which is now an established result in physics, would affect your thinking about this? For example, indefinite causal order should be experimentally accessible through a setup like this.
I didn't go that far. I'm a simple hardware man. I put 2 boards on a PC, measured them like this after a lot of software work. More, I guess my point with this presentation is more like your point is like there's things that can be explored with this kind of precision, right? And so my goal was to make it easier to reach that realm of like picoseconds, as opposed to like White Rabbit devices, which are like tens of thousands of dollars each or something like this. Whereas the total cost of this card, including the fabrication, is like $500 or something at low volume. So it was more like, okay, indefinite causal order or other things like that need hardware to kind of back it up, or something, you want to build to do something with it. So I was saying, okay, well, here's a building block that can get you down into these kind of domains. at relatively low cost that you can also scale depending how what precision you're looking to scale at.
Very good. Excellent.
I think much cheaper, Julian, like
Yeah, much cheaper.
much cheaper, like probably under $100.
Well, I said low volume. So
Yeah.
I was buying like 5 boards at a time or 10 or something. So fabrication cost plus BOM, something like 500-ish.
All right, any more questions? All right, hearing none, we'll adjourn and we'll see everyone in 2 weeks where we have a presentation by Ben Cope about a revolutionary approach to video wall processing architecture supported by precision time protocol. All right, see everyone in 2 weeks.
Thanks, everyone.
Bye, everyone.